Okay, so now we're getting into the last part of chapter 3, and that gets into stoichiometry, limiting reactants. So stoichiometry is just the idea of taking a balanced chemical equation and using it to determine, you know, amount of products, amount of reactants, all kinds of different calculations. But when it comes to a balanced chemical equation, that's like the first step, right? And you're balancing the number of moles as well as the number of molecules. So the amount of atoms you start with at the beginning has to equal the amount at the end when you balance a chemical equation. So when you get to when you're solving, typically you're going to have like grams of a substance or the measurable component, right? Whether it's grams of a substance or maybe it's liters of a liquid or liters of a solution. So you also need to know the molarity in that case, or you might even know like the volume of a gas. But so all of those measurables are given, and then you need to convert whatever those measured values are into moles. So you may use molar mass in the case of if you have grams of a substance. If you have a solution, then you're probably going to use molarity. And if you have a gas, you're going to use a gas at STP, you're going to use 22.4 to evaluate that. So the idea being that you have this starting with the mass of a substance A, you can use the ratio of the coefficients of A and B to calculate the mass of substances. And so this is where you set up your cancellation, like how you cancel a calculation in such a way so that the units you start with get canceled and the units you want to end with is what you go to. So using the dimensional analysis with stoichiometry calculations comes in quite handy when you're kind of working through, especially a long problem. And we will obviously practice these in class for sure. So example being, so we've got glucose combining with oxygen to or basically glucose being burned, and you get carbon dioxide and water. So first step, you've got 1 gram of glucose. You're going to convert that into moles by multiplying it by the ratio of number of moles and the molar mass in such a way that you cancel the grams. And I'll set this up in class a different way. I don't necessarily like it with the arrows, but if that works for you, you can use it that way. And then the ratio between the glucose and the water is a 1:6 ratio because you have that balance equation there. So we're going to use the different coefficients, so the 6 and the 1, to convert from moles of glucose to moles of water. And then the last step to get it back into grams of water. That's kind of the final answer that we're looking for. Okay, so now kind of the last component, or the way that stoichiometry is often used or is applied, is in limiting reactant type problems. And this is the idea that, so I've got this material here, I've got butter, I've got sugar, I've got flour, I've got milk, I've got eggs, and I want to make cookies. What am I going to run out of first? So if you kind of look there, looks like we've got a lot of supplies except sugar is what we're really low on. So we're kind of waiting. Once this family runs out of sugar, there's no more cookies. So the sugar would be defined as the limiting reactant, and then all the other materials are defined as excess reactants. So in a limiting reactant problem, you use the smallest stoichiometric amount. So whichever one we're going to run out of. So in this example, we're talking about like numbers of atoms or molecules. And so in this example, we have 10 hydrogen molecules, 7 oxygen molecules. Well, the ratio of hydrogen, when hydrogen and oxygen come together, is a 2-to-1 ratio. So you're going to be able to make 10 water molecules and have 2 oxygen molecules left behind because you only need half the oxygen as you do the hydrogen. So the oxygen in this case is the excess reagent or reactant. And then an additional piece when we talk about limiting reactant problems and things like that is something called theoretical yield. So when we do reactions in laboratory, we never actually get the maximum amount that we were supposed to get. We're very it's very unlikely that you're going to have a complete reaction where everything gets consumed perfectly. And so um, when you do stoichiometry and predict how much product you should produce, that is that's what we call the theoretical yield. That's like if everything if everything reacted perfectly, we should have this much product. Now, very rarely do you actually get does your actual yield end up being your equal to your theoretical yield. And so when we look at the two, the numbers are going to be slightly different. And so what we often do is calculate percentage yield by taking those two values. So the theoretical yield is calculated through doing stoichiometry, knowing what your starting materials were, and then predicting what the product should be. And then your actual yield would be the mass of your product at the end of the reaction that you achieved doing the laboratory work. And then, so with percentage yield, it's the idea of you find the yield based on your actual versus your theoretical yields. And so it's just taking actual yield, divided by theoretical yield, multiplying it by 100, and that gives you your percentage yield. So how close to the theoretical yield did you get? So technically, percentage yield should always be less than 100% in a calculation. There's definitely laboratory experiments that you end up getting percentage yields that are higher, but that's based on often significant error that occurs throughout a laboratory experiment, and you end up getting some really off values. So that's it, and we'll see you in class tomorrow.